So with that, let's go ahead and get started. I am happy to have Yuka Klemola, and he had me practicing that before we started, and I probably still butchered it pretty good, but nevertheless, OH6 Lima India with a great presentation on receive antenna metrics, and he's got some examples to go with it. So let's go ahead and get started. Yuka, it's yours. Go ahead.
Thanks, Ken. Great to be here. You can hear me?
Yep, you sound fine.
Good, good. Yeah, so let's start. That's me on the screen. I'm building there something at my one of my ham shacks. But the topic of today is receiving antenna metrics, and I'm going to show some examples. So what we're going to talk about is that, okay, what is there beyond gain and front to back? So those two terms are familiar to everybody, but let's see what there is beyond those. What Ken said about these practical things first, so let's start with the practical things. So I think this is going to be a little bit longer than typically seen on Worldwide Radio Operators Foundation webcasting, but all the antenna model files, Excel workbook that I'm going to show here, they will all be available via the WWROF pages. And like Ken said, as you have questions, please write them down. Presentation is long, and we're going to have that break. Ken is going to select one or two questions just for the end of the break, and then let's start with a short Q&A, and then continue with the presentation after the break. So great to be here, everybody. So the contributors to the presentation have been Markku West2RA, Dan AC6LA. Dan is a very famous person, at least to me. He's author of the Auto EZ or Auto Easy software that goes along with EasyNet. Frank W3 Lima Papa Lima, everybody know him, and he's very knowledgeable about receiving antennas. He has given me a lot of questions, a lot of advice with these topics that we're going to cover now. Reino OH3MA, he's a really great friend. He knows a lot of different technology areas, and especially from the super high frequency antennas, but he has been now on retirement, so he has been digging into the short waves as well, and also going down in the spectrum. Mike Delta Juliet 2 Queen Victor was contributing a little bit from Germany, and then Ward N0AX, he gave me a couple of questions, and that steered my presentation, but I have managed to put it together with Ward's insights and let's say order of things to present and how to present. So Ward was giving me a lot of advice on that. So then to the presentation, the contents. We're going to see the traditional metrics briefly. We're going to look into the receiving directivity factor. Most of you know it, but nobody has seen the directivity merit figure before, the DMF. Then completely something new is noise margin. I think people who have been dealing with the receiving antennas, everybody have been thinking that, okay, what is this noise? Is this electronics noise or what? I'm going to try to answer that. Then I invented something new, something else that is new. It's leaking index. Let's see what that is. And then I'm going to have a couple of suggestions for you people, and also to myself. So I'm talking also to myself because I'm developing my contest stations. So I'm going to think about receiving antennas for residential locations and also quiet rural locations. And then at the end, you're going to be astonished with the linear inline receiving array, what that is, what that lira is, other than Italian old currency, you will find out. So antenna gain. We're looking at antenna gain, which would be 7.41 decibel over the isotropic on the minus side. So now we are looking at 1 point in the whole direction pattern, the whole antenna pattern, and we just take one small detail. Maybe we are a little bit misled with that one little detail, and we should be looking at this phenomena more holistically. So antenna gain maximum, when we look at the 3D picture, it gets even weirder in a way that we are looking at only one point in the whole direction pattern. About front to back. So this antenna has 16.1 dB front to back, and it's in the direction of 180 azimuth and 40 elevation. But if we look at this part of elevation, it's still in the rear, it's still in the back, but the front to back is worse there. Over here, it's much better. So how do we quantify all this phenomena? How do we bring this into our real numbers instead of just having two numbers? And again, with this, when going to 3D, it looks even poorer analysis to have just two numbers to describe our antenna and the antenna characteristics. Let's start with something simple, something that is cardioid pattern. This kind of pattern you will get from a half wavelength beverage on ground or flag or 2 times ground plane antenna that are phased. And you will get also this kind of, let's say, gain numbers like minus 34 decibels over the isotropic or under the isotropic. And by the way, all these antennas that I'm going to show are on 160 meters, unless I say separately that now this is 80-meter antenna. So we are accustomed to look at these 2D or nearly 3D pictures like minus 3 dB points on the pattern. We have the azimuth, everybody know about this, but not many have been paying attention that, hey, there is more to it than just the takeoff angle. So there's a variety of angles that are forward looking, and there are 3 dB points. But there's more to it, so that now if we would look at this everything and think about the receiving, which one would be considered better direction? Is it this sector here on the right? Or is it something in the rear? So the point of view, or the, let's say, the angle of getting into the subject, my thinking goes with the receiving antenna, so that what we are attenuating, that's more important than what we are amplifying. And to be honest, we are not really amplifying anything with this kind of minus 34 dBi antenna. So there is a big sector in the rear that is minus 6 dB or better. So we are attenuating these guys while we are trying to hear these guys here in the front. And minus 12 dB, there is also a sector. We could go like minus 20, minus 30 dB sectors. Well, with this particular antenna, we don't have a too wide minus 30 dB sector. It would be there in this takeoff angle area, and it would be pretty narrow. But everybody wants to have their receiving antennas built in such a way that we would have a clear separation between what we are listening and what we're not listening. We want to get rid of the QRM. We want to get rid of all noise that comes from anywhere else than the direction we want to receive. So now let's go to modern metrics, the receiving directivity factor. It's maximum gain divided by average gain. And we are calculating it through the full hemisphere. So this is not a ball, this is a half ball, this is a hemisphere, because there's ground. And if we are looking at decibels, it's maximum gain minus average gain. And this RDF is available in a couple of softwares like EasyNEC, AutoEZ, and also 4NEC 2. Some people may have both of these, but what I have been using has been MMANA, and in this MMANA software, we don't have this RDF as such. So that was one of the accelerators for me to start building all this, these tools, what we're going to see later. So RDF is largely thanks to John DeVoldero and for you, and maybe also WHAI Tom has been contributing to the work or to inventing this RDF. But this is introduced in John's book, Low Band DXing, in chapter 7. And RDF is a 3D numeric calculation because it is taking into account all angles and it's calculating the average gain. Then something new. Directivity merit figure. So DMF is maximum gain minus back half average gain. We are omitting now what is in the front. So we are calculating as the bed. We're taking on the minus side only this back half, and we are averaging that out. And it's calculated. So it means it's calculated through back half hemisphere. And it's compared to the maximum gain. And this is a true 3D item, and this has been in ON4UN, John Devildeer's book, in the same chapter as the RDF is. So these are closely related, but I haven't seen this DMF available anywhere, but it is in this presentation. I'm going to show some let's say surprising figures that okay how these two are going to relate between each other. So now then the question is, what are these metrics good for? At least for me, the way for me how I have been trying to explain to myself that okay, what do I need? I have had some questions that I haven't been able to answer. So I have been figuring out that okay, how do I write down the fundamental questions? So I put it this way: that does my system hear noise from the band, or am I limited by electronics thermal noise? I think many have been thinking that okay, which noise am I hearing? Is it the band or electronics? But now, like we have people, like in southern Florida, there are people logging 300 countries on 160. And they are doing all that logging, all those QSOs with really small antennas, like receiving antennas. So my question there is that how small my directional antenna can be and still receive the noise from the band. So I'll try to answer that. And then the question that goes to the leaking index, which is that which antenna pattern is better. So much about metrics. So metrics haven't been developing too much like the DMF. We don't have it. We have the definition for it, but we don't have it currently. But within an hour we will have it. So I will show you how it goes. But the receiving antenna development is that we are striving for small antennas. People are in residential areas, even cities, and they are trying to operate 160. So these small antennas are, in other words, like they're flag, FO0AAA, kind of delta antenna, double CAS, different kinds of phased antennas, ground planes, and systems of ground planes. So the question, the technical question, engineering question is that we need to try to optimize the antenna size. We need to understand that how to evaluate or how to quantify the properties of different antennas. And I'm going to have a solution proposal for everybody in this presentation. And then most antennas, they do have side lobes, and pattern may leak despite overall average is good. So like this RDF and DMF, they are calculating somehow overall averages. And when I have been analyzing these antennas, I have been getting inconclusive results. So I had to develop something new. So I'm going to present that as a proposal for everybody to use in this presentation. So what there is typical about these new modern antennas, they are like beverage. They have a negative gain in dBi, and they are using a load like a resistor to form the pattern in a way or another. And then this brings to us a need to design antenna system level sensitivity. So we need to understand that antenna system, where we are, we need to understand the QDH properties, and we need to understand the gain, the average gain, and how it all relates to directional patterns and so. So then we can receive, but then to optimize the best signal to noise ratio, we are going to get by cleanest pattern, of course, but also we need to have adequate amplification. We need to have enough gain, enough average gain to be able to perform really well with our receiving antenna. So transmit antennas, they are going to integrate all noise, and they are kind of limited only by gain max or maximum gain increasing. So they don't have lossy elements, but these new antennas with the resistors or whatever loads they are using, they make the pattern by other means. So if the antennas are developing because of questions we have for the antennas, then the metrics have to follow. So there has to be antenna metrics development as well. So like we are right now using, we are using the computers. These wonderful devices bring us new opportunities. And we do have true 3D pattern data available. And kind of my chain in all this was question to idea to need to requirement and then to specification. And at the end, the calculation itself, it's easy. It has been pretty difficult to kind of understand the fundamental questions that, okay, what do I want to try to measure? What do I want to try to analyze? And then, okay, what do I do with this data? How do I change or how do I turn that into knowledge? So going ahead with the antenna pattern data. So these antenna simulators like ESNEC, MMANA, or 4NEC2, they are producing a sample-based 3D pattern, and we can input that into Excel. But then I happened to bump into Dan AC6LA, so he made an automated input for MMANA table angle gain. And then he made that for ESNEC, and just a couple of days ago he got 4NEC2 code done so that we can input also the 4NEC2.pf3 files into the Excel calculating machine. And to clarify, if you don't know what these softwares are, maybe words MiniNEC and NEC are more familiar. So this MMANA uses MiniNEC or a version of it with some enhancements. And then ESNEC is using the NEC like 4NEC2 is. So what we are getting in is that we are getting the zenith, azimuth, and gain at 1 degree resolution, 1 degree intervals throughout the half ball, the hemisphere. So first we are normalizing everything to steradians, and hemisphere surface is 2p steradians. That's just a detail, but it's kind of it's giving to you an idea that, okay, there's a lot of calculations behind all these numbers that we're going to see. So we need to get the data into metrics to evaluate, to analyze. So we are getting the average gain so that we can get the RDF, and we are getting the back half average gain to get the DMF. So how does this receiver antenna metrics workbook function? So first of all, we need to have the comma separated values file inputted into the Excel, and it happens on this kind of dialog box here. So we can select mmana.csv, and in the mmana simulator software, when we are building the gain, angle and gain table, the dialog box looks like this. So you need to put their step size and number of steps, then for zenith or the elevation and step, and then the number of steps. So how the algorithm is built, it's done so that we are using 361 and 91 steps. So it's like n+1 steps, and we are calculating the first and the last one, half of those. So the sphere is full, and also the elevation, it's like full 90 degrees. Then about inputting the ESNEC or 4NEC2 files, just tick here and then tick here and select the file. So there's a short description how to do it. Then the outputs. There are a couple of sheets on this Excel tool. So there's average gain, RDF, and DMF sheet. So it's the first one. It's kind of a front page. So this antenna here seems to be like number 6 of my antennas that I have analyzed. It's beverage, 250 meters in length. So it provides, or it produces, a maximum 3D gain minus 4.6 dBi. The average gain is just short of minus 17 decibels, and the RDF is 12.2. So now comes something new to most of you, that the DMF for this beverage is 20.1 dB, and the back half gain is minus 24.7 dBi. So the RDF algorithm is same as in SNEC. Dan has done those both basically, and DMF is now available for the first time as a new item. Then the outputs, so noise margin. This should interest many people. So first of all, the noise margin is noise level plus average gain, which is negative, by the way, typically, then minus 3 dB, minus feed system losses, minus receiver noise figure. And the noise level is the first one that we need to understand. So this noise level is the first we need to understand. We have a document from ITU explaining all those to us and giving us numbers. So on 160 at a quiet rural receiving site, we are considering that to be 46 decibels above the zero level noise, which is the Boltzmann noise, or the absolute minimum possible thermal electronics noise. And then for residential receiving site, on 160 we get 64 dB, and then same numbers for 80. And if you read this couple of words, if you can see those small letters. So the noise margin estimates if the receiving system is limited by electronics thermal noise. So we need to have the antenna's average gain big enough to hear the band noise over the receiver's thermal electronics noise. It sounds tricky, it is, but now with this Excel tool we can handle it. The other output for this receiving Antenna Metrics Excel tool is leaking index. So leaking index tells how much the antenna pattern leaks to unwanted directions or from the unwanted directions. And user can set the azimuth range here. The default is going to be 80 to 180 degrees, and zenith range is fixed 0 to 90, just because of simplicity, so that the equations, the algorithms would have become a little bit too difficult. And the metrics are built this way so that the antenna is better when smaller proportion of pattern leaks, and any leaking is attenuated more. So the less the antenna leaks, the smaller the leaking index is going to be. And here is a box that tells how it's calculated. And by the way, about these yellow boxes here, that the user is supposed to be giving numbers here. So we get the noise level from this document explained here. Then there are feed system losses, like I estimate in this table like 2 dB, and receiver noise figure 4 dB. So this is like a typical good transceiver front end. If you want to have lower figures or lower numbers, you would need to use a specific preamplifier. And in this case, we're just above the zero noise with this antenna that happens to be a sample for this screenshot. So then I wanted to have this kind of table where we are building up with our data, so that if we analyze a 170 meter long beverage or 250, or we have some fancy twin triangle antenna, I wanted to get these numbers here so that I can compare it with ease. And then this length, width, and height, these are manually input into the Excel table, but these we get automatically from the calculator. So it makes the comparing easier. And then if you have an archive somewhere, it's easy to copy paste all these data sets to a collection workbook. So now digging into these new antenna metrics in more detail. So noise margin, where do we get the noise margin from? How do we calculate it? How do we evaluate it? So first of all, the sky provides noise, or the noise comes from the sky. And it's mostly man-made, so the strongest noises there are, they are man-made. And then there's thunder, of course, but atmospheric noise coming from a distance, that is less severe than the man-made noise. But let's see how we can take that into account by mathematics. Then directional antenna receives noise by calculated average gain in relation to full hemisphere noise. So the amount of the noise depends on the location where you are. That's the same thing in other words. And then smaller antenna with smaller amplification receives less noise total. So to hear the weak signals, the noise level received from the sky through the antenna system must exceed the noise of electronics, the thermal noise, by a margin. So thus the word noise margin. So the fundament is that we can calculate the noise power we receive and how we receive it. Then thermal electronics noise, that is practically same as noise figure of the first preamplifier in our system, whether it's the transceiver preamp or some extra device, external device. We want to have a small yet highly directive antenna and receive the smallest possible signal. So that is what we want. So we want to hear the band noise at main lobe minus 3 dB points, and we want to have the smallest antenna we can. Especially the rural, like residential or city people want to have that. Then there are people who can afford a little bit more land area for their antennas. But in order to achieve all this, we need to understand and evaluate the antenna system noise margin. So the noise level chart looks like this. So this is from ITU document P372 and version 13. This is these numbers, they come from I would say from 70s. They haven't been touched since, but we all know that the noise, the electromagnetic noise throughout the world has been increasing. So this is a little bit optimistic or pessimistic, depending how you want to look at it. But this curve A is for city people, then residential is B, and rural is line C here, and then absolute quiet rural somewhere very, very far away from anything like, I would say, Bouvet or this kind of QDHs. They would be in this quiet rural category as described by ITU. So let's look at the 160 meters. How much noise do we have there? So the absolute minimum noise that there should be would be like 46 decibels, but this is a statistical figure anyway. So it may be that there are times that the noise goes lower. So here is atmospheric and man-made noise summed together. And then going to a residential area, the noise level increases by 18 decibels. So it's 64 decibels for this residential area receiving site. And the validation for these noise levels comes from ITU. And then for 80 meters, it would be there. So there are different numbers that I wrote to the Excel tool. So I said that this D is something that it's kind of a minimum noise level expected. And these are more statistical things, these curves for city or residential or quiet area. And in this document, in this ITU document, there are statistical decibel numbers for different areas that, okay, what kind of safety factors or safety margins do I need? So they are partially explained there, but nothing goes into ham radio direction with this accuracy that we have in this presentation. So about the noise distribution, when we are putting together an idea of a directional pattern of the antenna and the noise that is coming in. So in this calculation, we are first dividing the noise level that we are getting, this 46 decibels or 64 decibels, whichever. So we are distributing it through the sterady and surface elements over the whole hemisphere. And then just for simplicity, we decided that we will kind of split it even, or we will share it, we will splash it even throughout the function. So there is no weighing for low or high angles in this equation that we have. So I did build a noise mask, but in the Excel, the file size grew from about 5 megabytes to more than 8 megabytes, and it was getting slow, at least on my machine. And I just was thinking that is it worth the extra time that the Excel is calculating? So then we had a discussion about what is dominating. So the low angle man-made noise is dominating, but then to think about the directional patterns, the absolute low angle elevation, like from 0 to 2 degrees, the elevation gain is small, and it attenuates the low angle noise, and kind of it lowers importance. So this is kind of an excuse, but I wanted to take this excuse because I don't want to feel too bad about not having this mask. And then when I tried this low angle emphasizing noise mask algorithm, it showed about 0.38, 0.45 dB difference, and I was thinking that okay, if I try more, I wouldn't get more than 1 decibel difference anyway. So currently it's like this, but the noise margin algorithm can be improved by the noise distribution at least, so that how the noise is being distributed to the system that we are evaluating. So let's calculate. Let's see how this builds up. So we are calculating in decibels for the residential area. We have there the noise level, and then we are taking the gain average of the antenna and we are adding it. But as the gain is negative, it builds downwards. Then we subtract the feed system losses, couple of decibels, and this gives us the noise level at antenna system output connector at the main lobe maximum point. But then we want to hear the -3 dB points, and we subtract another 3 dB. So now in this graph, we are reaching like 20 decibels of noise, and we started with the 64. So there has been like 40 decibels or more than 40 decibels of loss. So then we are looking at the receiver capability. So it builds from the bottom, and this shows our receiving system capability. And here in this case, it's about 8 dB, just so that we can see the orange rectangle there on the chart. Okay, and now voila, we have the noise margin. So the noise margin is the empty space between these two. And noise margin gives room for noise level changes. Like these are statistical things, and they go a little bit up and down. So noise margin tells us how reliably we can receive the band noise over the thermal electronics noise. So noise margin in this Excel tool, this RX Ant Metrics, how does it look like? So first of all, we took the noise level from this document, and it's 46 decibels would be the minimum needed number for 160 meters. And then we write there the feed system losses and the estimated receiver noise figure. You can measure it, but not many people know their receiver noise figure. And the distribution around the median value curves is described in radio noise document table 2. And the noise margin really should be several decibels to achieve good antenna system performance in all conditions. So there are people who are saying that, okay, 3 dB is enough, 6 dB is enough. You need a little bit more than 10. So there are many kinds of people, and now that we can start to quantify this, I think that we can get maybe in a year or so, we can get to a point in the discussion that we will say that, okay, this is the margin that we need, but currently we're just guessing. And about the receiver noise figure, it's typically from 3 to 5 dB, and preamplifiers like W7IUV or some commercial preamplifiers, they do have smaller numbers. But now understand that there's no way you can improve your system to infinity by lowering the noise figure. So lowering the noise figure is going to have a limit, so that going beyond like 2 decibels or 1 decibel, there's no point in it. You cannot do wonders with this. It's just an amplifier. So the feed system losses, that's all losses from all transformers. There are cables, connectors, relays, filtering, and that is between the antenna feed point and the first preamplifier. Then if you have a proper first preamplifier, that's all you're gonna worry about. But if your preamplifier is somehow marginal, then the calculus becomes more complex. And then this minus 3 dB comes from the requirement to be able to receive the front lobe minus 3 points and everything in between. About leaking index, let's look at that in more detail. Leaking index tells us how much the antenna pattern leaks to unwanted directions. And the default was from 80 to 280 degrees azimuth. And the antenna is better when we are receiving smaller proportion of any leaking that is attenuated more and more. And we are calculating percentage of leaking at 3 levels. That would be like a gain maximum minus 12, 18, and then 24 decibels. You will see soon on a graph that how this builds up. And the leaking index is the average percentage of leaking at these 3 levels. So let's look at this cardioid, this flag kind of antenna again, the pattern. So we have the limiting angles. There is the azimuth, there's the elevation. So now what we're doing is that we are comparing the gain maximum to anything in this volume. So this is not area, this is volume now. And it's more than just a hemisphere or half of a hemisphere. So we're doing the calculation at 3 levels. So it's like minus 12, 18, and minus 24 decibels. And then we are adding it all up here, and we are getting percentages that, okay, how much does our flag antenna leak? So it would leak 76% in the average in this case. And that would mean that 76% of any QRM coming from the rear will come through and disturb you. So the smaller the leaking index is, the less the QRM from the rear is going to vary you, or from the sides. So the fundamental difference to DMF from this leaking index is that this goes a little bit beyond the sides, so that we can calculate, we can take into account by mathematical means any leaking from directly from sideways. And DMF is a little bit more limited in this nature. So in this tool, the user can set the azimuth range unevenly to support asymmetrical antenna patterns like phased systems. And the maximum gain direction must be roughly into the direction of azimuth 0, not exactly, but roughly. And then the default values are there again, 80 and 280. And as a comparison, the DMF calculates from 90 to 270 degrees. So leaking index bottom line is that RDF and DMF, they are at the end, they are general averaging calculations, but this leaking index brings up only the amount of leaking. We are interested only in the amount of leaking and how much it is. And we are calculating more than just the back half. And this is configurable for narrow main lobes. I will show you at the end of the presentation what that means. Leaking index can be the final decision maker, so that when I have been analyzing now or playing around with these numbers for a couple of days, or well, about 2 weeks, I have had this tool at this level that I can analyze stuff. So I have been rethinking some of my antenna choices I have at my stations. So leaking index does have limitations. So it's currently limited to 0 to 90 degrees elevation. And the forward-looking high elevation angles, they are not counted in. So if there's any leaking coming directly from front direction, like azimuth 0 or close to it, then we are not counting it in this equation. But currently, I haven't found any antenna that would model in such way that this algorithm wouldn't find the leaking, because the leaking usually spreads to sides if there is something going into the front direction and upwards. And one of the weaknesses, or one of the limitations, is that this leaking index strives to improve the pattern to minus 24 dB level, not further. But I think that's not a big deal. That's not a big problem. You will see that at the end of the presentation. And also this leaking index algorithm, like there are weaknesses, we can improve it. But for the simplicity of the mathematics, time of the calculations, it's such that we can improve. Okay, we are to Ken. We are exactly on schedule. So let's take one example. So various antenna examples are going to be shown. I don't remember how many, more than 10, maybe 13. And there will be new antenna concept, maybe 2 new antenna concepts to most of you, but at least one that very few people have seen. So we're going to have a look at this kind of triangle or delta that I call FO0 AAA antenna. Then we're going to look at least 2 or 3 beverages, twin triangle. Then we are going to look at something new to everybody, like linear inline target X antenna. What that is, I will reveal shortly after the break. And then there's staggered beverage, which is currently the benchmark antenna. And then we have a newcomer, linear inline receiving array. What that LIRA is, it's going to be exciting. So let's go through the first example and then have a break there. So this kind of simple triangle, I saw emails about this kind of very simple but good antenna for the receiving. I got the first messages about this from Earl K6SC on some top band or some antenna discussion forum. So it's not a flag, it's not rectangular, so the ease of feed point, so we will go directly downwards with our cable from here. and then we have a load placed somewhere in the rear. And this is really a nice antenna. We don't have to worry about ground connection too much, like with beverages. We have to hammer something into the ground. But with this antenna, we don't have to worry about such conductivity or these issues just about at all. So this triangle that we're gonna see the numbers for it, it's 5.5 meters tall, like 18 and 4 in US metrics. The bottom wire is gonna be up 3 meters, like a decent size deer can walk freely under it, and not the biggest moose. So if there's gonna be a big moose, it's gonna tear this down. But it's the bottom wire has been calculated or modeled at 3 meters height. The bottom wire length is 8 meters. That's like with the US measures, it's 26 and 6. The construction width I estimated to be 3 meters or 10 feet. And the wire for this antenna, just it happened to be 4 millimeter copper when I just pressed the go button on the simulator. And then in the literature, there has been a lot of fuss about load, but you don't have to worry too much about the load. Anything between 820 and 850 ohms will do, and you will place it somewhere around here, not in the corner, but some percents along this leg upwards, and you will get a little bit better pattern than having the load exactly at the corner. And the feed is going to be 800 ohms, and this is going to serve you very nicely, this kind of antenna, if you know how to make the transformers and cut a little bit from the common mode interferences. And now something for all antennas. So dielectricity and conductivity are going to be 13 and 3 throughout the presentation, or all these models. So this is very close to this FO0 AAA triangle or delta antenna, like K6SC described already like nearly 20 years ago. But now we're going to have metrics for it. So the pattern looks like this, and we get now the RDF. This is same as you have seen for this kind of flag antennas, but now here's something new for everybody. So the DMF number is 12.8. And the back half average gain is minus 47.4 dBi. The noise margin for this antenna at a quiet rural location, very far away, is going to be minus 5.4. I wouldn't worry too much about it, but we need to take into account that this noise margin should be positive at least by a few decibels, like I would say 5-ish. So this is like 10 decibels short of being a good antenna or perfect antenna at a very far away location. But now let's see what comes to rescue. So 64 decibels at the residential receiving site. So this was the rural number and the quiet rural, but now for the residential, we can see that the noise margin is more than 12 decibels. So this kind of antenna can be considered to be a good top band receiving antenna, and it was only 8 meters in length. And it all comes down to the noise level that we have at residential receiving sites. And this is going to be much better than any ground plane, any dipole, any inverted V, depending where you are pointing it, especially where you have that attenuating sector on the rear, which wasn't too wide. So this minus 5.4 dB to 12.6 difference comes from change from quiet rural to residential. Then leaking index. Leaking index with this azimuth range gives like 56.9% at the minus 12 dB level, and then going to the average, it's like 76.7%. So how this relates to other antennas, we will see after the break, but here's the first comparison table. Like the noise margin is the only figure changing here because we changed the QDH from 46 decibels to 64 decibels on the noise level. Okay, Ken, are you there?
Yes, I am. So you ready for a break?
Good. Okay. I hope I was making sense. Let's have a break for 5 or 6 minutes, okay?
Yeah, okay. So everyone, what we'll do is we'll take a 5 minute break here. It's going to be a hard 5 minutes because we want to keep this thing rolling. We'll come back, and I've got a question or two here. Maybe we can take one other thing I want to mention. If you submit a question, please put your call sign with it because all we get is the name, and we don't necessarily get your call sign attached to it. So that would be handy. So, all right, 5 minute break, and we will be right back. Recording again. Okay, so our first question comes from Guy, VE2 Bravo Whiskey Lima, and he's wondering on the triangle antenna, is it susceptible to nearby lightning induction as much as a one wavelength beverage?
Well, if we look at 80 meters beverage or 160 meters beverage, there's 80 meters or 160 meters wire conductor. So now what's going on? Okay. So if we look at this kind of antenna, that's like 8 meters here, 5.5, 6 meters like vertical. This is going to receive much less energy from any lighting. So any kind of thunder is less of a problem to this. But if you're going to have your coax here and it goes to your receiver and it's connected to the receiver, then any nearby lightning, it's going to burn your receiver front end pretty surely. So this is not kind of a thunder protector, but this receives much less energy from that kind of electrical or electromagnetic fields that are such certain occasions.
Okay, just hold that slide for 1 second. Another question popped in here quick, as long as you've got that up, from my friend Dave, K3 Zulu Japan. Is that the triangle antenna broadside or end fire in its direction?
Okay, that's a good question. Hi, Dave. This direction is such that this is shooting that way, and it's attenuating that way. So this is attenuating through the left, and this is kind of receiving directly from the right. So this kind of antenna is described also in the John's ON4UN's book, and you can find instructions about this and models just by using this FO0AAA search word on Google.
Okay, last question, and then we'll get started. Comes from Stu, V2 X-ray. X-ray was wondering why the ITU used a 1 hertz measurement. It's really not realistic, being that even on CW we use 500 hertz bandwidth. Would this not show at least a minus 30 to 35 dB error and noise measurement?
It's for science people. So what we're dealing here with, this is true science, and I'm trying to do my best to simplify it so that we will get some sensible numbers for us to be able to, let's say, evaluate, analyze our receiving an antenna system. So in this equation, let's see now. In this equation, so what I have done here is that I'm using that 1 hertz bandwidth from the top and from the bottom, and then we get in decibels the noise margin like this. So this is a lot of this is a huge simplification for us. So I'm trying to be here kind of a little bit like I'm a fan of Mythbusters. So I'm trying to make this like everyday living, but at the end, this is really deep science what we're dealing here with.
Okay, very good. All right, so why don't you go ahead and roll on with your presentation. Just reminding you we are at about an hour here, so continue on.
At about an hour, oh boy. Okay, let's see. So we were left here. We were left with an antenna that has a noise margin like this, with this kind of QDH noise levels, and DMF is now the new figure, and this RDF, everybody recognize this 7.5 to 8 dB RDF for this type of antenna. But DMF is now completely new, and also the noise margin is completely new, and it's based on noise level at the QDH. with the QDH properties, and then leaking index. I think this is the worst antenna that we have here, this single triangle. But now that we had this minus, what was it, minus 5.4. So we had minus 5.4 with this kind of triangle that was 8 meters in length and 5.5 on height. So let's increase the size of it. So let's make it like 50 feet long, 25 high. And now these are exactly like, these are feet. These are not like inches or any quarters or eighth parts of inches. So these antennas are really easy to build. And the load can be something like this, and then you will go to WAJI or W7IUV webpage. You will figure out pretty easily how to feed it. You will just buy some amidon toroids and some wire, and off you go. You'll be happy with this antenna. So noise margin is now 2.1. So this is like 7 decibels or 7.5 decibels better than the smaller triangle. And now this is a good antenna. This is getting to be a good antenna, even if you are somewhere in the middle of ocean. So let's see, let's compare these. So RDF, it's basically the same. DMF, basically the same. But now we have this third antenna here at a quiet location with 46 decibels, showing us a little bit positive on the noise margin. This is not exactly the best possible antenna, but this is the smallest I would build for top band at a very remote location, to be able to kind of hear the weak signals. Like if I would be somewhere far in Pacific and I would try to operate Europe, I would build this kind of antenna there. This is very simple to do. Lightweight to carry, very robust, no breaking parts. Then let's see the residential guys. So I was promising in the beginning that here's going to be something for the let's say the average people who live in suburbs. So here the bottom wire length is just 5 meters. Is this any good? And the triangle height is just 3 meters, like 10 feet. So the construction total height with the bottom wire being at 3 meters, it would be like 20 feet. And same applies here. There are no such things like 751 ohm resistor. No, we don't need that. We need something in this range. So now let's see what we have. The noise margin for the residential guy is 3.4 dBs on 160. This is a good figure. Remember, this is now a 5 meter long antenna, and the total height is 6 meters, like 20 feet by 20 feet, and that's it. That's all you need. And your leaking index would be like 75.1. This is still in the same range, but now remember the size of this thing. This is a very small. And then if we look, if we take this same small triangle that is 5 meter in length, and we check that out on 80 meters, how does it work? So we get noise margin of 6.6 decibels. So this is getting to be a decent antenna on 80, and it's only 5 meters long. This hears much better than any ground plane. I guarantee that. If you build it by instructions on these pennant sites, and so if you take any advice from there, this is going to be a super receiving antenna for everybody at rural locations. So this just about functions there. If you can build it a little bit longer or taller, like the first example was with this 8 meters long bottom wire, it's going to be a little bit better, but that's getting kind of a big antenna for any suburb where the property areas are like let's say 40 by 40 yards or so. So where I'm living, our property is like 45 by 35 yards. So Beveridge 170 meters is the next one. Now this should be an eye opener. So you saw this direction pattern already earlier, and now we get for this the noise margin 19 decibels. But the RDF is much better. So of course, sorry. So that this 19 decibels is of course much better. But now remember, this is 170 meters long antenna. That's like 180 yards, 185 yards. And the RDF is 10.6. This is better than the triangle antenna, but this is not that much better. So if you would be in a residential area and you would try to build this kind of beverage there, I think you would be in trouble with neighbors and maybe also the county officials. But this 5 meters long antenna, it's going to be nearly as good as this. Not as good, but you can at least convince yourself that now I have a directional antenna if you build such triangle. And now we are getting just a reference number 17.2 for the DMF. And then the leaking index, the interesting part. So in this directional pattern in the rear, we can see there's a area for -12, -18, and -24 decibels. So the previous leaking index was like 75, and this is around 50. So this is much better antenna in this way, because there's side attenuation. If you remember the other pattern, it was sideways. It was showing something like -3, -5 decibels attenuation on the sides. But this is roughly how a beverage of this length looks like. So this is going to be a better antenna in every way, but remember the size. Then let's look at a longer beverage. So this leaks a lot from sides. This leaks a lot from rear, but now look at it again. There's no third. So this leaks at -18 and -24 decibel levels only, and this leaks upwards at this -12 dB level. So the leaking index drops 7% units. This is a big drop when the percentage is getting this low. So this is almost clear on the -12 dB level. This is much better antenna than the 170 meter long beverage. So this is now confirmed. But remember that this analysis or this model has been done on MMANA, which uses a little bit unorthodox ground model. So this is a theoretical, theoretical model only. Not many antennas would function like this in real world. But anyway, now the beverage show their power compared to the smallest antennas possible. So I mentioned earlier that there's this kind of twin triangle. What that is? So we have two triangles in a row. So this is not a broadside. This is inline arrangement, and this radiates to the right, and this attenuates from the left. The total construction length of this animal is 58 meters, which is about 190 feet, a little bit short of 200 feet. The bottom wires are again at 3 meters. The bottom wire lengths, so this triangle and this triangle size is 24 meters. So this is like 10 meter separation here. So 10 meters of just air. And the loads would be somewhere in around 850 ohms. So then if you would feed this at 800 ohms, you would get this, and with this kind of 0 and 180 degree phasing, which is very simple to do, just connect the coaxes differently. So the braid and the center connector goes to that side in the left, and the other way around in the right antenna, and just couple them together, and it will produce this kind of pattern. And this is now a 50 meter long antenna. So we're getting like a gain of -23.33, but the average gain is -34.5. And look at the RDF. This is 1 decibel better than with the beverage. The DMF breaks 20 decibel mark. The noise level, this is amazing. This is like a very short antenna, and we get positive noise margin at very low noise location. And then the leaking index, this is the best part. So this kind of antenna shows really nice pattern. So 12 dB or better attenuation level is wider than the leaking index default 80 to 280 degrees. So this does not leak as much as the 250 meter long beverage. I repeat, this does not leak as much as 250 meter long beverage. And this is just a short, much shorter antenna. So leaking index is 41.8. So we're getting closer to a low kind of good numbers here. But now let's pay attention how these metrics behave. Like I said, that this leaking index can be the decisive factor or decisive number when we are starting to split the hairs and I'm trying to decide that, okay, which one is better. So RDF got worse compared to this 250 meter long beverage. The DMF stays the same, but there is a small change in the leaking index. And of course, because this is much smaller antenna, this is like less than 200 feet long. So it's like 1/3 of the size, less than 1/3 of the size, maybe, yeah. So this is a really small antenna compared to this beverage, and we are getting the same numbers practically. And this is on the limit, this noise margin, but it's not too bad because people building these will be living in civilized world, not on some deserted island somewhere where this kind of 46 decibels noise level would be found. So like with the triangle or this FO0AAA, what I did, I was trying to find a solution for the residential guys or residential hams. So the total construction length of this antenna is 25 meters. Let's see how it works. Pattern is the same. I didn't believe this when I first did this simulation, but then ESNEC did confirm this by OH2RA, and we were both astonished that, hey, this looks nice. So now the most important measure to me with this is I'm jumping always to this noise level and the noise margin. So now we take this residential area noise level and we get a positive number for the noise margin. This is not bad. Making this like 30-35 meters long will increase this further, or making these triangles a little bit higher. So it will increase this number if you want to. But this is something that I could recommend for anybody who can put up a antenna that is 25 meters long. This is not a bad choice. The leaking index is now below 35% mark. So this is pretty good. The RDF is 11.5. So RDF shows that this is worse antenna, but DMF shows that this is better antenna, and leaking index verifies this is better antenna. Let's see, now this jumped there. So smaller twin triangle, we are getting worse numbers for RDF. DMF is 1.7 decibels better than the 250 meter beverage. Leaking index is on a planet of its own. It's like minus 10% in relation to this 250 meter long beverage. And noise margin is positive. So this is not a bad choice. Then if we look at the smaller twin triangle on 80 meters, on 80 meters for residential area, the noise level would be 56 decibels. And the noise margin is over 10 decibels. It's 12.5, the machine is suggesting. And the leaking index is below 40%. So this shows pretty nice numbers. And just for clarity, if you compare these numbers, there's residential and quiet rural. So the numbers are like this. So this is for 80 meters. So this would not be a ideal antenna for quiet rural, but people living there, they will have more space anyway. So they will build something bigger. So DMF and leaking index win over this long beverage for just residential guys or residential hams antennas after this. So you will be able to perform much better with this kind of antenna. So then these new concepts. So LIXA. So OH6 X-ray alpha is my friend and a long time friend. So this is named after him, and kind of putting the LI there in front was natural for me for some reason. So I have built this kind of proto at my summer home. So this is just short of 23 meters. I don't know why I ended up with this kind of number, but this is how it's built. And this here, the bottom wires are at 2.4 meters, just for me being able to climb there on short ladder a little bit easier than up to 3 meters. So I have been doing a little bit work with the feed point and also with the load, of course. And then the structure is such that here's a triangle, which is same size as the front triangle, and there's open wire feed line in between. So this thick part here is a open wire feed line. So I'm feeding this two triangle thing with one coax. This is a very simple antenna, and it produces this kind of pattern. So this reminds like DHDL or double delta pattern, and the noise margin would be minus 6.3 decibels if I would be somewhere in a quiet rural location. But I'm somewhere in between, let's say, rural and quiet rural. So my noise level is somewhere around 50 or a little bit above that. So my noise margin with this antenna is close to zero. Leaking index is back up a little bit more than 45%. The RDF is just short of 10, and the DMF is 20. So this has a little bit better pattern than these two antennas, and I have been testing with this, and I have been happy with this antenna. And I have another version, like a rectangle version of this double triangle construction. So 2 times Lyra. This is named after the great idea generator OH2 radio alpha, and I call this linear inline receiving antenna. So we have 2 LIXAs, and the total construction is like half a wave on 160. So this is 83 meters, and it does this kind of pattern. If I wouldn't have this tool now here that mutes everybody, I would have heard a couple of wows. Look at this, and look at this also. So this is really a nice pattern for this kind of a less than 100 meters long antenna. So noise margin for absolute quiet rural place is just about 0. The leaking index it's now rock bottom, which is 4.6. So this antenna does not leak from unwanted directions. RDF is just 12 decibels, but the DMF is now breaking the 30 decibel mark. So this antenna's total land area really is 83 times 3 meters. So this is really a nice antenna if you can build this. We have built one prototype that has been now up for more than a year without problems, and it's pointing to South Americas, and this is performing very nicely. On the same property, there's a group of ground planes, and this simple antenna works really nice there. Then the staggered 320 meter or 2 wavelength beverages. on top band. So with this my ANA analyzer or simulator, I get this kind of pattern for it. So noise margin is of course big because this is a huge antenna. The RDF is like on WHAI or K7TJRP web page. It's like something between 14.5 and 15 decibels. But now the DMF is 25.9. Remember what we just got for 2 times this lira? It was better. And the leaking index was 1/3 of this. So the RDF is now a benchmark. So this wins over the single 250 meter long beverage there. So RDF is now more, 2 decibels better, nearly 2.5. But now if we look at the DMF, the lira is better. If we look at the leaking index, the lira is, or 2 times lira is much better. So this 2 times lira gives a good challenge for any antenna imaginable that we may try to build. And it's just on a land area of 83 by 3 meters. And here's the picture in the middle of field in southeastern Finland. So this is not in southwest where I live. This we just put this up at a friend's place in southeastern Finland like a year ago in December. So then this is the last antenna that I'm going to show. This is the maximum performance receiving antenna. This is 4 times lira, and it produces this kind of pattern. So this doesn't really break through minus 30 decibels on the rear. So there's one side lobe, but also this can be fixed by correct phasing and voltage in the feed. So this is like 4 lixas in a row. So this is like 2 liras just after one another. And I repeat that you will get the model files for these from the WWROF pages. So you don't have to try to figure out that, okay, how Jukka did it, but you can just input the model and see on the screen that how this was done. So RDF is the same as the 2 times 320 meters long beverage. That is, by the way, the construction width of that beverage, the staggered beverage, is exactly 100 meters in the model. The DMF skyrockets, it's 37.6. This is a huge number, and somehow I believe in this number. The noise margin is, let's say, okay. This is not perfect, but this could be something smaller if you make this a little bit shorter, or a little bit bigger if you make this a little bit longer, this arrangement. I think if I remember correctly, this was 216 meters long, and the leaking index is now down to 0. So 4 times lira brings us a 0% leaking index, even with azimuth from 70 to 290 degrees. So this is way over half hemisphere. And we get to 1% level at 50 and 310. So those of you who have been modeling these antennas, you can say now again, wow. So as comparison, the DMF is whooping 37.6 decibels. If you think what this means that the average gain in the rear is 37.6 decibels below the gain maximum. This is a very clean pattern. The noise margin is positive and the leaking index is pure 0. So I announce now that this kind of 4 times lira is searching for a test location. So I bet that this would be excellent usage for 216 times 3 meters land area. So the length of this antenna was 216 meters when the other one was 350 by 100 meters. And the height of these triangles would be only 13 meters, by the way. So now if we would be maximizing our own QDHs, I'm trying to sum this up now. So the new tools open up new possibilities in finding the best alternative for everybody. So if you have a big land area to improve, there is room, and now there is also an opportunity for improvement. So we have found something new with these simulators. And if you have a smaller land area, now you have a couple of recipes how to improve. So I really suggest that you take the trouble to set criteria, compare, and then build it, and then operate. Please operate. Be on the bands. The bands are surprisingly quiet during the weekdays outside the contests. So as a final conclusion, one or two numbers alone, they are, or it is a too simplified way to look at these receiving antennas we're dealing with. The noise margin is now a new amplification metric, and for pattern quality, we have a number of different figures, like there's takeoff angle, there's gain, RDF, DMF, leaking index, and now we have also mathematical means to use any combination of those. And the receiving antennas develop, and the metrics also develop with the computing capabilities. And I'm just expecting to get a version of some MMA-NA or SNEC that would be optimizing against DMF or leaking index or whichever of these, but kind of automated optimizing, that would be the next step I'm after. So Ken, if you are still there.
Yes, I am.
Thanks for listening, everybody. And now I would be ready for some questions. I hope I'm just in time.
No, you're doing very well. No problem at all. And I commend the attendees as well. We haven't had but one or two people drop off, and it could have been for technical reasons as well. So everyone's hanging in there. Okay, I have two questions. If anyone else has a question, like I said, go ahead and put it in the questions box. You can click on that and pop it out. Put your question in and hit send, and we'll pick it up here and pass those along to Yuka. The first one comes from Ash, 3 Victor 8 Sugar in Tunisia. When we are assessing antenna performance with different configurations, what do we need to consider, RDF or DMF, especially if they are diverging? He says, many thanks for the very interesting webinar.
Okay, I would put it. I would put this very simply. Take this Excel tool and look at the leaking index. That will be the decisive factor. That will tell you how it's going to be. And this Excel tool will tell you also if your system is sensitive enough, so if you can hear the band noise. So this will tell also that. And then after that, it just comes down to your preamplifier, that if it's functioning as it should, then you will be okay. But if you are getting like mixed messages from RDF and DMF, then use the leaking index. So that will give you the right choice.
Great. All right. The next question is one I am interested in, and in fact, it comes from my neighbor, Mike, K4GMH, just down the road from me. How does the LIRA, L-I-R-A, work in wooded areas with trees? Because this area, we have tons of trees, and my receive antennas, my transmit verticals and everything are amongst trees, and I always read how it's detrimental. And I do own a chainsaw, but I am also married and prefer to stay that way. So what can you tell us about that subject?
Okay, my friend OH2 Radio Alpha has done a extensive check with simulators and trying to get a grip of idea that, okay, we have ground planes, we have this kind of other vertical antennas. By the way, these loops, what we are discussing now, or what I have shown, they are all verticals. Also, the beverage is vertical in polarization, in case you didn't know. So they are okay as long as a tree doesn't come too close. So if a tree is touching your aluminum or copper wire that is not insulated, it's going to affect your antenna, especially when the tree happens to be moist during a rain or some kind of very, very heavy fog. So then you will have a problem. Then if the if the distance is like 10 centimeters, like 4 inches or so, the effect or the problem is kind of there, but after 2 feet, 3 feet of separation from the tree to the antenna wire, you're okay. So if you have a large vertical metal object like a power line or telephone wire coming down from a pole directly in the front of this kind of antenna, then it's going to affect you, even if the wire is like I would say 40 meters away. But this kind of short wires that are 10 yards or less than 15 yards tall, I would say that if they are in rear of antenna, they can be as close as just 3 to 5 meters from the antenna if it's in the rear. But if it's on the side, it's like I would keep that kind of metal structures more than 10 meters away, and then in the front it should be pretty clear. So you have this same kind of thing that many people call re-radiation. So if you are beaming towards a large metal structure, you can get some problems, but with trees, I would say generally no problem.
Okay, very good. Yeah, because every time she goes out of town and she comes home, the first question is, how many trees did you cut down while I was gone? So, all right. Next question comes from Andre, Radio Alpha 6 Lima Bravo Sugar, and he's wondering if you've.
Hi, that's a familiar call sign.
Okay, good. Well, he's wondering if you've had a chance to do any of this metrics with well-known receive antennas like 4 squares or 8 circles, and how do we know real-world performance of those antennas? Well, we know them very well, and I'd like to compare the theoretical figures. So have you done any of those types of antennas? The 4
No,
square and the, like the 8 circle.
My MMNA is limited in that sense. I haven't gone into the direction of ground connected ground planes. So the Earth model in this MMANA is limited. My friend OH2RA has been doing some analysis with the verticals, and his results are good, but I didn't want to take any of that into this presentation because this was like hour and a half already.
Sure.
But as long as the radiation patterns are roughly the same, and the maximum gain, and then if you compare two antennas, you can do it in such way that you take the radiation pattern and then compare the gains, and that will tell you a lot.
Okay, very good. Another question from Charlie, Kilo Charlie 9 Lima Alpha. He says, once again, super presentation. Do you have any insight from a physics or electrical standpoint why small antennas seem to act like directional couplers with respect to wave travel, and this is output towards the wave arrival, and beverages that are the opposite? And does this potentially provide any clues to improving small antenna arrays? Hope you got that.
Yes, so it's like the beverage. It's a transmission line. So beverage is a transmission line, and you will get in the signal from one direction, and then you will input that into your coax, and then the signal coming from the coax direction, it will be deleted by the end resistor. So it functions roughly that way. But these antennas, these function in a different way, and it's just to me, I haven't taken the time to learn any of the deep detailed mathematics behind these. So my experience is limited pretty much just to this simulator work, but the antennas that I have been talking about here, one important point now popped into my mind. So I showed you the triangle, the first triangle, that it was 4 millimeters copper. It's like more than 1/8 of inch thick. It's almost like half-inch copper. Sorry, quarter-inch copper. So these other antennas have all been 4 millimeters aluminium, which is almost like a quarter-inch aluminium, and that's thick wire. If you try to build this from thinner wire, you will be in trouble. It will not work because the losses in the wire are going to contribute so much that it will distort, or it will destroy your pattern. But with beverage, you can get away even with iron wire, I think. So there the losses are less significant. But with these small antennas, the losses in the antenna structure are very important. But then if you look at the transformer that is between the antenna and the coaxial cable, then the transformer itself, it can be very thin wire, but the antenna wire, the antenna construction of these small loops, it has to be thick and low loss. I think I answered only part of your question. So sorry I couldn't give a comprehensive answer.
That's fine. Okay, so let's take one final question here as we wrap things up from Stuart, and I think his call is V2XX. He's wondering, how does the FO0AAA antenna compare to like the Waller flag? Do you have any thoughts on that?
Waller flag essentially is like a twin triangle. So if you compare these antennas to Waller flag, to JC's antennas, JC's antenna, what he has been building is like let's think about the vertical Waller flag. So it fundamentally operates like this, like these twin triangles out of this presentation set, what I had as examples. So it is much better. So the Waller flag it's from different planet. Waller flag directional pattern, let's say the quality of correctly built Waller flag exceeds the performance of 200 or 250 meter long beverage. So it's a great antenna, and just one simple triangle or delta will not match it. Then if you go to horizontal Waller flag that is up more than 150 feet, I think it has to be like 40 meters or so up. That antenna is going to bring another step in performance. So JC is thinking that how the horizontal antenna receives less man-made close by residential or city area noise. JC is an expert on that, and kind of that horizontal Waller flag takes the game to the next level, which is very close to 2 times Lyra, which was several tens of meters in length. But then with the Waller flag, I have seen only one Waller flag in my life. That was a horizontal one at Austin's Nancy Ford Whiskey's QDH in South Florida. So that seemed to me like it was less than 20 meters long in boom, and so it's a good antenna for that kind of residential or let's say dense residential location. So there the noise margin performance should match the surroundings, but if you live somewhere like deep in countryside, from close to I think, yeah, if you're deep in countryside, then the Waller flag can be limited by noise.
Okay, very good. Well, let's go ahead and wrap this up. Anything else, Jukka, before we close her down here?
I really like the questions. I like the audience. I like the arrangements. I don't know, Ken, how you can pull this every time so that this is so good, high quality surrounding to give this kind of webcast presentation. I like this very much. And now here comes one bit from me. So how to build these antennas? I'd like to give a presentation later in the spring when we don't have snow anymore here. So let's see if we can have a presentation how to build these.
That would be wonderful. You let me know when you're ready, and we will do that.
Okay.
Okay, well, I would also like to thank the Worldwide Radio Operators Foundation, WWROF, for sponsoring the webinar. They're the ones who pick up the tab for the GoToWebinar program and bring a lot of good content. And guys and gals, you could put in a heck of a lot of work on this presentation, as you can see. And I want to thank you, Yuka, for all the work you've done and for your willingness to share this with us. It's a lot of good stuff, and certainly a topic that a lot of people are interested in. I know I certainly am as well. So thank you for all of your efforts. Once again, we will post the recording and any other material that he wants to pass along on the WWROF webpage. It'll be under the webinar archive link, and we'll send out a notice as well once that's up. But hopefully in the next few days or so, we can get that taken care of. So with that, thank you everyone for joining us. Have a great rest of the week. Hope to see you on the bands. Yuka, thank you once again. 73s, everyone. So long. Bye-bye.